Have you ever imagined what it would be like to optimize effortlessly? To transform complex engineering challenges into simple, elegant, and functional solutions? Meet Adria Portero, Marina Balinchin, and Oriol Gomez, industrial design engineers and master's students at Elisava. Today, they invite you on a journey through the redesign of a high-performance motorcycle's triple clamp, demonstrating the power of Altair Inspire software. Let's dive into the technical heart of our project. We'll begin by setting up our design environment. Let's get started. Initially, we isolate the component of interest from the larger assembly. Next, we carefully select and configure the material, ensuring it aligns with automotive industry standards. Moving forward, we begin by addressing our first load case scenario, focusing on the forces endured by the triple clamp during hard braking. Before applying the loads, we set up a custom orientation system to facilitate precise load alignment. This system takes into account the 25-degree incline of the fork. According to telemetry data, this scenario involves a braking force of 2,000 newtons and a weight normal reaction of 3,000 newtons. By configuring our simulation to reflect these conditions, we aim to closely mimic the actual stresses experienced during intense braking maneuvers. Once configured, we simply connect the force points that are applied to the internal surfaces of the side clamps. This accurately simulates the stresses the triple clamp experiences in a real hard braking scenario. Understanding that the triple clamp will endure dynamic forces under adverse conditions, why not create a second load case to observe its behavior during cornering? Let's set up a new system, but this time incorporating a 45-degree curve inclination. In this scenario, we'll assume the triple clamp experiences a lateral force of 1,000 newtons and a weight normal reaction of 2,000 newtons. Once the dynamic forces for both scenarios are configured, it's time to add the shared static forces. We'll assume a force of 15 newtons at each joint for the headlight mount and an additional 5 newtons for the auxiliary rear attachment. Now that all the loads are in place, let's proceed to the main constraint. We'll apply a support that completely locks all degrees of freedom of the piece, simplifying the simulation experience. Furthermore, Inspire allows us to efficiently and easily organize the load cases and select the forces. Now that our setup is ready, let's start the simulations. First, we'll look at the braking force results. The program shows us how the fork tube's force creates bending moments, with stress peaking at just 49 megapascals. Since the safety factor is well above the minimum, our design is over-engineered, suggesting we could reduce material without sacrificing safety. Comparing this to the cornering analysis, we see stress levels increase by 75%. However, given the minimal displacement and a safety factor of 2.8, this presents an excellent opportunity for topological optimization. After observing the component behavior, Inspire enables us to intuitively partition the design space for optimization. Specifically, we can segment and select the bridge section that connects the clamps, all within Inspire, streamlining the process without needing additional software. Now we've reached the most crucial moment, leveraging Altair's optimization capabilities. By evolving through several iterations aimed at maximizing stiffness and minimizing mass, we arrive at a shape that holds significant interest for the team. This optimized design is then subjected to the initial braking force analysis to ensure its viability. The results provide a highly intriguing insight, showing a mass reduction of over 50% while maintaining a safety factor of 1.6 and an extremely minimal maximum displacement of just 0.33 millimeters. The success of this final analysis allows us to move to the last step and developed the final solid using the poly-NURBS tools, crafting a design that not only meets but exceeds our engineering objectives.